Hello, everyone, and welcome to the Weekly Space Hangout for Wednesday, December the 6th, 2017. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about Voyager 1 firing up its thrusters after 37 years, plate tectonics on Europa. Has dark matter been detected?
No.
And the spoiler alert! And the here comes the Gemini meteor shower. So joining us this week, we've got I choose. Let's see. Oh no, it's going to go straight to. I'm going to have to go to our guest first. Our guest is Dr. Brian Koberlein. Welcome back to the show, not as a panelist, but as a special guest.
As a special guest. Thank you very much for having me.
Which means you probably got some really interesting project to talk about.
I do a little bit, yeah.
Yeah, okay. All right. Well, as well, we've got, let's see, let's go with Kimberly Cartier, the Earth and Space Science reporter for EOS Magazine. Kimberly.
Hey, Fraser. Hello, everyone. Happy podcast day.
We've also got Dr. Paul M. Sutter, an astrophysicist at Ohio State.
Keep working on it.
And host of Ask a Spaceman. Paul.
That's right. Thank you so much for having me on.
All right, so before we get into this week's show, I want to remind everyone, as always, to join the Weekly Space Hangout crew. This is, of course, the group of fans who work with us every week to put the show together. They're our executive producers. Brian Koberlein shows up on the show. Although I'm pleased, I didn't know it was going to happen, but I'm ready to interview him. And that's all thanks to our executive producers at the Weekly Space Hangout crew. If you want to participate in that, go to wshcrew.space and they will hook you up. All right, let's get on with the special guest, who's also a panelist. This is very strange in my brain. Special guest, Dr. Brian Koberlein. Who are you and what do you do?
I'm an astrophysicist and I work at Rochester Institute of Technology. I blog called One Universe at a Time. And I'm developing a TV show called Big Science.
What? Oh, man. We've all just got like a YouTube television show. What is this real television show that you're working on?
So this is trying to do a pitch to networks. It started off as a conversation amongst a friend of mine and I, and then made contact with a Canadian production team who has now been working with us to develop it. And then we did a Kickstarter and we asked for funds to film a pitch video at Green Bank Observatory. And we broke through the level that we needed and then some, and are now currently in the production of the pitch video at Green Bank.
That is awesome. So tell us what Big Science is going to be about.
So the basic idea of Big Science is to look at these large research facilities from the eyes of everyone behind the scenes. So if you ever see something like CERN or Green Bank or any of these large facilities, you're probably talking to the head of maintenance or the chief scientist or something like that. And we're actually looking at all the background people who are actually doing the heavy lifting, who are in the thick of it, keeping it up and running and doing the actual science from the back end. And so it's looking at the whole culture and community around one of these big science facilities. And the idea is to look at several of them across a season.
So what are some of the facilities that you're hoping to add to your list?
Well, we've got, a lot of ideas. Green Bank is one of them. We could look at everything from CERN, ALMA, the large telescopes like that. We've thought of things like Goulion Castle, where they're actually creating a castle from scratch using medieval techniques to look at how that was done, from an archaeological standpoint. The whole range of everything.
Okay, so it's not just your special field of particle physics and astrophysics and things like that. You're talking about Big Science across all of the fields.
Right. So it's facilities that take a large collaboration asking big questions about the world around us and the universe that we live in.
And so Are you just being cagey here? Tell me where you're going to go. What do you want to look at?
We don't have a final list yet. In
Well,
fact,
let's
we can't
imagine
have
you were like pitching at me some places where you think big science is getting done. You mentioned someone building a castle. That's cool. You mentioned Green Bank. What would be on your bucket list of places where you think that that you would love to show people behind the scenes? I know, like you went down to South America, to Chile, to see the big observatories down there. What are some other places where you think people would be interested?
I guess some of my bucket list places, Chilean astronomy would be one of them, just because that's my field. The Galapagos would be one that would be great, because it's a microcosm of our planet in terms of how do you maintain the ecology as well as having a thriving economy where people can live. The seed bank that stores all the archive of seeds. The Antarctica, you really want a bucket list. I want to go to Antarctica, but that's probably not in season 1.
Right.
But the idea is to give a wide range view of how we do science, why it matters, and that science isn't just these elitist people with PhDs who are working on it. They require this large infrastructure of highly skilled people who have to work, under tight budgets, both financially and by time, to keep things up and running, to keep everything working, or the whole thing fails. It all falls apart if you don't have this large community.
I mean, I think that there are, when we think about how like a house gets built, we understand the hammer and the saw, and we understand the tools that construction people will use to be able to actually build what they're building. But when we think of how science gets done, the scientists are using a tool. They're using, be it a gigantic telescope or something that's smashing particles together, or something that is burrowed into the ice to be able to find secret magma vents on Antarctica. Like it is this, it is huge, but they're tools. And so I think that's a really fascinating way. And most people, because these tools are in remote locations and are incredibly complicated, and people are busy using them, we don't get a chance to go behind the scenes and see what's going on. So I think it's a great idea.
Yeah, I mean, it's when you start looking at this kind of back end of things, you see this entire engine of just incredibly skilled people, being incredibly innovative just to keep things going. There's all of these secondary problems that you don't think about when you think about, any of these research facilities. So to give you a couple of examples, there is a neutrino detector in northern Minnesota. And one of the issues they have to deal with is bats, because it is in a mine about a mile deep, and bats will go into the elevator tunnel that goes down to where the mine used to be and now is the neutrino detector. And they have to deal with the white nose fungus. They have to prevent the bats from having white nose fungus. And since they're endangered, there's a whole group of people who are looking at the environmental impact of the neutrino detector on bats. So you think this is just a neutrino detector, but they all have to deal with this.
So tell me about what it's been like for you to actually pitch a television show. You did the crowdfunding, which I don't know of a lot of television shows that go through this process of building together a fan base to try and help get the thing funded to a certain stage. Is that fairly unusual and unique in this process? I haven't seen that very many times.
I think it's becoming more common, and it's particularly more common when you have something that's a little bit unusual. One of the things that really struck me was we went down to Green Bank to do research. So after we got the crowdfunding to do this, because it takes a certain amount of money to film on location and do the actual research, because you have to meet with people and set up meetings and schedule everything. And you have to at least have a skeleton crew to get there when you're doing even just the research, not even the filming. And so when we went down, these are people that, everybody does some short episode on Green Bank. Let's look at the radio silence zone. Let's go talk to the people who think that it's affecting their brains or something, and it's the same story. When we went down there to actually talk to people, the thing we constantly heard was, I'm so glad you're actually doing research on this. Everybody else just buzzes in from DC, spends 2 hours, captures some video, and goes home. And that's the hard part. That's the challenge that we have to have with the crowdfunding and with the fan base, because we have to convince a studio, look, this is going to take time. It's going to take effort. But what we're going to get is going to be unique and rewarding in a way that other shows haven't done. And we're already seeing that. And the people who are, this is not their first rodeo with the television crew, and they're seeing our difference approach.
That's interesting. Maybe you just don't have enough experience.
Yeah, well, I certainly don't, but the people I'm working with do.
Yeah. Is that like the people who are working on like Daily Planet and shows like that? There's a, as a Canadian,
there's a wide range.
Yeah,
They've done a lot of Canadian television and some American television. So they're award-winning television people. So they're highly skilled. And, in some sense, I feel like the upright dog in the room, because, it's like, oh, wow, I can look you up on IMDb and, okay, I watched some of those things. Nice to meet you.
Yeah, to actually meet the people behind the scenes that are working on those projects that you've really enjoyed. So what happens next? You've shot a pilot. How far have you gotten?
So we haven't shot a pilot yet. What we've done is we've done all the background research. We've done some location shooting to frame out what we actually want to film at television quality. So, you have to go down. If you really want to see what you're going to film for something at Green Bank, you have to know what's there and what you can film, because there are limitations. Part of it is because Green Bank, for example, is a radio quiet zone. So if the telescope is running, you can't use video equipment at all, because it's radio loud. Yeah. All your cell phones have to be off. You can't use video equipment. So the only way you can film at the telescope is to have it in maintenance mode where you can get access, and there's this whole security thing you have to go through. And then you have problems like the guy who's directing, who goes down and is scared of heights. And then we're going to go up to the top of this radio antenna, and he's a little nervous about stepping off of the gangplank, which he did great. He was fine. But, there are all these little things that you have to do. So we are at the point of, we've done all the background research. We're finalizing the treatment of the pitch. And now it just depends upon timing and weather. So we're either going to film very soon, or we're going to film in early spring, because as soon as it gets into deep winter in the mountains, you can't even guarantee getting there.
Yeah. And if all goes well, how many will be in the first series?
Well, that depends upon the studio that takes it. What we're filming is a pitch video that's kind of like a mini episode type of thing. And then that with the entire visual and literary pitch will be shopped to various networks. And that's what the producers and the directors do. And I sit here twiddling my thumbs, hoping that something happens soon.
Now, are you going to be the on-screen person doing a lot of the talking, or how's that going to work?
If I can actually do my job, yes. There's a lot to learn, because I'm used to doing a class, or I'm used to doing a podcast, and video is very different, and how you frame it and how you stage it, it's a whole new learning skill.
Yeah.
So I'm still learning that. A network could still say, this is great, we love it, we need someone 20 years old and cute, which is not going to be me. So that's always possible.
Yeah.
But right now, that's the plan.
That's
the risk.
Yeah.
So,
they'll go like, can we get Neil deGrasse Tyson? And you'd be like, well, that's it for me.
Yeah, pretty much.
Yeah. Yeah, absolutely. But I mean, we haven't had you on the show for a while, and partly because we've kind of changed the format. Also, you're always a busy person. In addition to this project, what have you been working on?
I've still been writing for Forbes. I've been, trying to work on a book and trying to put some of those things together, but a lot of it has just been this series pitch, and then I have kind of a high load for this term at our IT, so I've been focusing a lot on that. So I'm really looking to the holidays,
And what's a piece of research that's come out fairly recently? Because I mean, normally you would be contributing a story. What's something you've been blogging about just in the last couple of days that you're pretty excited about? But don't steal either of our other hosts' stories.
So I think one you didn't talk about was the new Distant Quasar. Is that right?
The farthest black hole that was found. Yeah. No,
that's
great. We were actually thinking of talking about that. So what happened?
So what they've observed was a quasar that was at an extremely high redshift. So it was about 600 million, 650 million years after the Big Bang. And it has when you look at quasars are not black holes, but they're all the material that's superheated around a black hole that gives off intense radio waves and X-rays and things like that. But by looking at the amount of energy coming off of a quasar, you can estimate what its mass is. Well, this thing is so bright that it has a mass of about 800 million suns. So it's 800 million solar masses, which, is on the large size of supermassive black holes, but is not extremely unusual. But it's really early in the universe. So 600 million years is when stars are just at the point of starting to trigger and form, and galaxies are just forming. And then you already have this massive black hole. And it raises interesting questions about how fast you can form a black hole. I mean, how do you get to 800 million solar masses in 600 million years? That's just an incredible amount of mass concentrated very quickly. And so this discovery kind of pushes back the idea that it's going to take a longer amount of time for them to grow. This is already full size, far bigger than the supermassive black hole in our Milky Way, which is only about 4 million.
Yeah.
So this is 200 times bigger than that.
Andromeda's is like 100 million.
Yeah.
So
this is huge.
800 million is just ridiculous.
Right. And to be that early, we wouldn't have thought that this was possible. And so the question then is just a rare fluke? Is it just that it happened to be forming in a very dense region of the early universe? Or are they more common? Do they form much more quickly than we had originally thought?
I mean, does it actually break the simulations? Like, does it actually break how quickly a black hole should be able to come together? Or, theoretically, like, I know there's like a limit on how much you can just feed a black hole until it just starts to...
Right. There's something called the Eddington limit, that basically, as you try and shove stuff into a black hole, it gives off all this light and heat and everything, and that will push back on the matter trying to get into the black hole. So it's kind of like a traffic jam. You try and put that much material very quickly, and that heat and pressure pushes back on it. So you can't, as far as we understand it, you can't break that limit. And this bumps up against that pretty quickly. So it's one of those things that we wouldn't have expected black holes to form that large that quickly. And now we're having to kind of look at these models to see how that's possible.
Well, that made me reminisce for having you here as a regular contributor. So don't hesitate to come back and join us again when you kick off some other big project, which you seem to do all the time. So where can people find out more?
You can find me at briankoberlein.com, which is the one university at a time. One universe at a time. One of these days I'll figure out my name. You can also find me on Facebook. And if you go on Facebook and look for Big Science, you can find a picture of me and see the Big Science website. And if you like it and share it, that's great for us because it shows a fan base and support, and we can use that to leverage actually making the series.
Right. And that's how I was going to ask is what can the viewers and the listeners do to give this show the greatest chance of actually happening?
Basically sharing and spreading as much attention as possible. The larger we can show the fan base, we've shown that people will support it financially. So now the next step, as we do this pilot development, is to actually show we can develop an audience. We have a fan base that's interested in this, that would be interested in watching it, and that's what's going to be useful to actually pitch to the studios.
Fantastic. Brian, always a pleasure. Thank you so much for joining us, and really good luck with the project. I can't wait to see you hanging precipitously off the Green Bank Observatory.
I've got pictures.
Awesome. All right. We'll see you later.
Okay.
All right. So now we're going to move on to the regularly scheduled portions of the show. Let's start. Kimberly, let's talk about Voyager 1's thrusters, fired up after 37 years.
Right. So after a 37-year hiatus, Voyager 1, its trajectory control maneuver thrusters, or TCM thrusters. They fired for the first time in 37 years. They fired perfectly exactly what the engineers wanted them to do. And what the engineers wanted them to do was to take over from the thrusters that have been functional since Voyager 1 last encountered Saturn. These are the altitude control thrusters, which are generally used for those tiny little short bursts of power that reorient the spacecraft so its antenna is always pointed back at Earth. But for Voyager 1, the altitude control thrusters have sort of been degrading for the past 3 or so years, and engineers at NASA were really concerned that it would limit the lifetime of Voyager 1. They thought, oh, it's nearing its end. Eventually, the thrusters won't work. The antenna won't be pointed at Earth, and that's sort of the end of what we can get out of Voyager 1. But then they remembered the trajectory control maneuver thrusters, which pretty much on Voyager were only ever used for the really large continuous burns during planetary encounters when it met Jupiter and then Saturn and sort of wiggled around a bit around the planets. That's what those larger thrusters are for. And then they just, were dormant for 37 years. But they said, what if we could use these trajectory control maneuver thrusters, the TCM thrusters, what if we could use them in place of the other thrusters that are sort of wearing out? And so they tested it. It took 19 and a half hours to learn that the TCM thrusters worked perfectly. And because of that, they're planning to actually switch over to the TCM thrusters for all of these little directional shifts that the craft needs to do. And we're going to get another 2 or 3 years out of Voyager 1.
So did we think that there's still some plutonium left in its RTG, so it can power it, but we thought it would slowly drift away and we wouldn't be able to communicate with it. And so it gives us 2 or 3 more years of communication lifetime?
Yes. So the altitude control thrusters have pretty much only been used just to keep the craft antenna oriented back at Earth. It's as it goes out, it encounters small little particles or a little eddy here and there that sort of gently bumps the craft and it turns or it wobbles or it rotates or something. And if the antenna is not pointed at Earth, we can't get the data back. And so that's what these thrusters have been doing pretty much continuously since it left Saturn on its way out to interstellar space. And apparently the other thrusters can do just as good of a job. They do require a bit more power, which is why they generally aren't in use. They require a heating mechanism to actually fire them up. But if you only use them in very short controlled bursts, something like 10 milliseconds in length, they'll do just as good of a job as the altitude control thrusters, and probably even better as the other thrusters start to degrade even more. You can use the bigger thrusters to do the same job. And then once you run out of the power you need to actually fire them up, the lower power thrusters can still continue to do the job that they were meant to do.
So now it's just a race against time then. I mean, if they're able to use the attitude thrusters to keep a connection to Earth, it's just a race against time until the RTG, the radio thermoelectric generator goes down.
That's more than I knew.
And that's when they can no longer communicate with Earth.
Yeah,
and they're going to start shutting down those experiments one after the other.
Yeah, once you can no longer course correct, some of the instruments might still be working, but if you can't transmit it back to Earth, it, sort of the end of the road there. But the cool thing is that now that they realize that the TCM thrusters can do the same job as the other thrusters, they can do the same thing for Voyager 2. Now, those AC thrusters are still working just fine. But now that they know they can also use the TCM thrusters to do the same job, we can keep using Voyager 2 even longer and get even more data. And that one might actually, eventually maybe go into interstellar space.
What are we getting data of? And I thought we had totally gotten into interstellar space.
Yeah, with one of them.
We were in interstellar space like 5 different times.
Yeah. Back and forth.
Now we're there.
Now we're there.
The one thing I would just... Oh, go ahead.
Oh, I was going to say we might be there, but go ahead, Brian.
The thing is, when we talk about this, what amazes me most is the ability to keep these things running. I mean, you think these thrusters haven't been engaged in 37 years,
Right.
which means there were people, babies born who grew up, went to school, went to college, got a job working on this project. And for the first time in their lives, this thing is firing.
That button on the dashboard that they've been looking at and wanted to press.
This says do not
for
press.
all these years. This is do not press. It probably doesn't work. They finally pressed it.
People talk about how harsh space is, but Earth's environment is pretty harsh too. Like, we have to deal with oxygen in the atmosphere. We have to deal with dust and contamination. Out in space, you just have radiation and cosmic rays.
Yeah.
So you can just build
micrometeorites.
Yeah, micrometeorites.
But they also demonstrate they're the first generational ships we have.
True.
They're the first spacecraft that have gone over generations.
The scientists
too bad they don't carry generations with them.
Yes.
Yeah. They had to go back into archives almost 4 decades old to find the computer programs, figure out what the heck kind of programming language was used back then to actually
encoded that on
do the test.
Yay, Fortran.
Yeah.
Hey, I've coded Fortran.
I know Fortran.
I know my Fortran too. Did anyway.
I'm useful.
It's one of those where
yeah.
Talk about legacy code, man.
Yeah.
But,
all the Y2K
So what
bug
data are
coders.
we interested in that's worthwhile getting for a few more years? Anybody?
Environment that exists at the edge of the solar system. We're learning about the heliosheath. sheath. We're learning about the edge of the sun's magnetic and gravitational influences. We're learning about all these different types of plasmas that could be happening right at the edge of the solar system. These are regions that we can't study very well or at all from Earth, even with the fanciest types of space telescopes that we may eventually launch. Cough, cough, next year, hopefully. Yeah. We can't study these regions unless we're actually there.
Yeah, I mean, there is this bubble that the sun is putting out that is enveloping out to this region in the solar system that is protecting the solar system and pushing away a lot of these particles. And this is the place where it can actually start to encounter larger amounts of those particles out there and make these kinds of measurements. And nothing else has ever been able to do it. I mean, it's still well within the solar system. When you think about the actual scale and how far out the Kuiper Belt goes and how far the Oort cloud could be, that it's still this teeny tiny little fraction of the larger solar system.
Yeah, so in gravitationally, well, I've such a hard time of, and I guess I'm not the only one, of picking a definition for interstellar space. Yeah, scale-wise, it's within the Oort cloud, but the Oort cloud's extends out maybe a light year, which is ridiculously far. And Voyager is not gravitationally bound to the sun, even though it's within the orbit of the Oort cloud and Kuiper Belt. And it is in this region where the solar particle density drops off and you just encounter the general interstellar milieu, the general mixture of all the stuff floating around in the galaxy. So yeah, scale-wise, it's not in the solar system. Gravitationally, it's definitely not in the solar system. Or scale-wise, it is.
How can you say, oh yeah, we definitely left the solar system. We're definitely in interstellar space. You don't even know what that means. No one knows what that means.
But I think the definition that they use,
here's the place.
It makes a good headline every couple years.
No. The definition that they use in this case, right, is that when you're within the heliosphere, the particles that you're experiencing are the sun's solar wind. It is this blowing wind that is pushing out this bubble, and as soon as you get out beyond it, then the vast majority of the particles that you're experiencing are the interstellar winds, which are blocked by the heliosphere. So
it's have you ever gone into someone's house?
It's a very interesting environment. Totally worth sending a spacecraft out to.
Have you ever gone into someone's house and you the house has a distinct smell to it? As soon as you walk in the door and you're like, oh, I'm not saying a bad smell. It's just, okay, this is someone's house. This is what their house smells like. And then you walk outside the house in this transition point between the smell of their house and the smell of the outside. And that's where the Voyager probes are.
House
I think
cells.
I like the gravitationally bound idea.
So
Because-
anything that's
because
not gravitationally bound is not a.
It's not gravitationally part of our solar system. It's leaving, and there's nothing we can do to stop it. So it's just a matter of time.
We get this really cool looking asteroid.
Yeah.
Well, yes, but that was a natural one, and we as a human species have been able to
But I think
make something an interstellar object.
I think that's a really interesting definition, because I don't think we would say that Oumuamua is a part of the solar system. It is a temporary visitor.
It's a visitor.
And it's coming and it's going. So I like your definition.
The Voyager is a temporary citizen?
So I think it's very easy to say that
It's an emigre.
Voyager probes and New Horizons, all those are no longer a part of the solar system because they're not gravitationally bound to the sun. But are they in interstellar space?
I didn't say that.
But there's also, I guess, the question of it's still in communication with Earth, and we can still control it from the solar system. So in that way, it's
but we
part
can't
of
stop
our
it.
Well, we could stop. Well, no.
No,
Maybe we could stop it. We can't turn it around and fire the thrusters.
we don't have
catch
to.
it.
It doesn't have enough thrust.
Yeah, we could catch it with a bigger spaceship. But
We
that's
can
about
shoot a
it.
giant laser at it and vaporize it.
Yeah. But then the vaporized particles would still be well on their way to wherever that star is that
There'd
it's
be
going
no
to.
more Voyager.
That's right. We got to have something for Nimoy to find. You
Right,
know,
of
the
course.
23rd century.
V'ger. All right, let's move on. Let's move on with Paul, your story for the week. Your first
Europa.
story.
Is that what you want me to talk about?
Let's talk about Europa first, and then we'll bring it back around.
Yeah, so I always love results coming out of simulations because simulations are awesome. And this is new simulations. There's always been suggestive, highly flirtatious, suggestive images of Europa that the ice sheet that covers this moon looks like it's fractured and it looks like it undergoes plate tectonics. There's things like ridges and subduction zones and fracture points. Exactly what the Earth's crust experiences. And now some simulations lead more credence to that idea that something is happening with the crust of Europa, that it's not a solid sheet of ice, that it is actually capable of forming plate tectonics just like the crust of the Earth undergoes plate tectonics, except at much lower temperatures because it's ice instead of rock. And these plate tectonics are driven by things like temperature and salt content, which can change the density of the ice, allowing one plate of ice to slip underneath another. So that's pretty cool, just general coolness about space. The other thing is there's all sorts of little organic compounds on the surface of Europa, like tholins. And when one plate slips underneath another, it's possible that this can go all the way down into the liquid water ocean. So if there's any organic materials or nutrients or metals or whatever sitting on the surface, it can go all the way down and reach the subsurface ocean, which would become food for the Europa space whales.
Right.
Yeah.
But
plus,
and also the alternative though, right? In that you would have other spots where cracks are opening up and space whales are surfacing.
Yeah, breaching.
Right.
Yeah.
Mm-hmm.
But I mean, like here on Earth, the fact that we on Earth have plate tectonics is not just good for feeding life and helping to start life and getting a good environment, but it's very important on Earth for sustaining life because it, like Paul said, it recycles all these nutrients from the surface, underground, through the core. And that was one of the really big tricky things with having life on a subsurface ocean planet is how do you get that sort of cycling of nutrients so that you can spark life probably pretty easily, but how do you get an environment that sustains it and nurtures it? And you need that constant recycling of material. So to find that there's, a good theory, a good model that matches what we see on Europa that supports that is really, really exciting.
And I really think that once they're able to send the Europa Clipper, once they're able to do some of this analysis of these pockets of water underneath the surface of the ice, we're going to get a much better sense on not only kind of how these cracks might have been forming in the past historically, but also some of the best places to go and send future landers and try and search for life. So it's quite amazing that all this research is kind of coming together at the same time that the right tool for the job is getting ready to be on its way to Europa to search for
And that's
all
a
kinds
really
of
good
tasty
point,
evidence.
because just how plates can subduct and touch the ocean, material from the ocean can upwell to the outer layers of the crust, which make it potentially accessible to us for investigation.
Especially when you consider the geysers that have been confirmed on Europa as well as Enceladus. I mean, now it's just like these places are doing the heavy lifting for us. So
yeah,
the implications for for Europa, for Ganymede, for Titan, for even Pluto, that ice tectonics might be viable. That's just like blows the whole habitability thing like wide open.
Well, there was a really interesting paper as well that just posted by Avi Loeb and friends about how it might be that these icy worlds are probably several orders of magnitude more common than the rocky planets that we're more familiar with. And these seem to be the perfect places to search for life. I mean, it's not just Europa and Enceladus. It's possible that there's liquid water even on Pluto under the surface of the ice. And so suddenly that's where you're going to be looking across the Milky Way, is these icy worlds, because that's where life could be holed up. Liquid water, nutrients, perfect spot to look.
Underground space whales.
Under ice.
Yeah. Under
ice.
Subglacial space whales.
Subglacial space whales. And the terrible, terrible space sharks.
Wait, no. No jaws
I
in
imagine
space.
there'd be a whole food web going on.
Yeah. And the space sharks that chase them.
The space whales have to eat space plankton.
I try not to get too excited about Europa, but it's something that brings out the kid in me, and I could go on and on of how potentially exciting it is. Of all the places in the solar system, this would be like the last place you would look, is the moons of the giant planets. And here we are finding ingredient after ingredient for what we need to make life.
But you add on top of that this idea that there are mechanisms that are bringing this stuff to the surface. It's just so great.
So we actually don't have to design a mission that drills on.
Yeah, all of those people that were working on nuclear-powered drilling machines can just stop and instead work on space noses.
Actually, they can keep working on that, because that's pretty awesome. I'd still like to see that.
Yeah.
And if we want to talk to the space whales, we have to go down to them.
That's right.
Good point.
So we still need the drill.
All right. So my story, and this is going to be fairly quick, and then we're going to get on to a larger conversation, which I think is going to be really interesting, that we're going to be able to get our two PhD astrophysicists talking to each other. But first, I just want to remind everybody that it's the Geminids coming up a week from today. So on the 13th and the 14th, it's going to be the Geminid Meteor Shower. And a lot of people consider this to be really the best meteor shower. This is one of the ones that brings the most meteors. In perfect conditions, you can get 1 to 2 meteors a minute, 120 meteors an hour, sort of in perfect dark sky conditions, which is really good. I mean, the Perseids, the summer one, they're great because it's warm and it doesn't suck to go outside. But the Geminids can be really fruitful, but it'll be a little colder, except for the Australians and the Argentinians. They're going to enjoy, warm skies as they watch the meteor shower. So if you have any interest, go out on the night of December 13th, I guess 12th, 13th. You want to look. Now they're going to come from the direction of the constellation of Gemini, but really you can see them anywhere in the sky. If you don't know your constellations, that's sort of like where they seem to be originating from, and they come from an asteroid known as 3200 Phaethon. And one of the cool things is that actual asteroid is going to be in the sky. so you can actually spot it. It's in with a telescope if you've got the instrument for it. So that's it. Just want to remind everybody, week from today, although you should be watching the Weekly Space Hangout, but if you're not, that would be a good time to go out and see the
Well,
meteor
you
shower.
watch Weekly Space Hangout and then you go outside
go
because
out.
the meteor shower sort of peaks. You know, it starts peaking around like 9 p.m. and 10 p.m. and that's after we broadcast.
Yeah.
You know, that's all good.
And-
You know, I've never seen a meteor shower. Did you know that?
What? I don't understand. Can
I'm
you,
a terrible astronomer.
you
I've
said
never
a bunch
actually
of
seen- I've seen
words.
meteors.
No, hold on. So you said a bunch of words that I understood, but you put them together in a way that really didn't hold for me. So can you say those words
Yeah.
again?
I'll say them slowly.
Yeah,
I
please
have
do.
never seen, Kimberly Cartier, has never seen a meteor shower.
Nope.
This is your lucky month.
No,
Yeah.
no,
Nope.
like
Still.
white noise.
No, I don't get it.
I've seen
Same here.
meteors, like a couple meteors.
Come
but like
on.
Yeah.
a sustained like meteor shower.
I stand with Kimberly. I have not seen a meteor shower either. I've seen meteors,
Yeah, of
Yeah,
course.
they happen.
Yeah.
but I've never done the whole meteor shower.
Brian's giving a look like
I have seen meteor showers several times.
Yeah.
You
What?
know, I live more out in the boonies, I guess.
What? Or
I mean, like
had an
when I lived
interest
in
the
central
night
Pennsylvania,
sky.
that would have been like the time.
I'm very interested in the night sky.
Yeah.
Well, it's the old
when
joke
it's
about
freezing
astronomy, you know. So you must spend a lot of time looking through a telescope.
Yeah.
Oh, heavens no, I'm an astronomer. I spend all my time looking at computers.
Yeah.
Like you must know all about, how to identify constellations in the sky and all about the lunar phases and
Yes, because it's still 1587.
it's one of those things where like we talk about it and we promote it to the public and you got to do all these things and they don't
I know my constellations. Oh man, so that's what we'll do, Paul. I'll teach you your constellations when we're on the cruise or when
I
we're in
appreciate
Iceland.
that, Fraser.
Yeah.
Yeah.
It's one of those things
Yeah,
where
and you didn't invite us. I mean, come on.
yeah. Well, Morgan and I have been hounding on them for weeks.
I
Like,
know.
that's how you
Put me
know
on that
whether
list, dude.
you're a PhD astronomer or not. Like if you know your constellations, you're probably not a PhD astronomer.
No, I do know my constellations.
Yeah.
Well,
and you
so-
have seen meteor
Brian,
showers.
you are special.
And I have seen meteor
So
showers.
and this is
Just stay tuned, Brian. Don't
the
worry about it.
Leonids, and I don't, Brian, were you there for the Leonids that came out back in 2001? I think it was.
Mhm.
It was like the sky was falling. You were seeing, several meteors a minute. It was unbelievable, and I think they had thousands per hour. And there are these times where you get these full-on meteor storms where you see just an enormous number of meteors. Like it really looks like, I don't know, Buck
Just
Rogers
coming down left and right.
Yeah, and that would be amazing. But I think just any meteor shower is a treat, and they are worth it. The key is you just have to find a nice place with the dark skies, get out there, prepare yourself, have the right clothing, have some people who are patient.
Hot chocolate.
And hot
Hot
chocolate.
chocolate. It's always mandatory.
Yeah, exactly. And this time of year, it'll get pretty frosty. So, but it's such a
That's
good
way
time.
too much effort.
Wow.
Isn't there who's the lazy astronomer? Isn't that someone's blogging handle, the lazy astronomer?
Oh, maybe.
Lazy astronomer. It is.
You could be the
Someone's
lazy
Twitter handle,
spaceman.
too.
If not, I'm claiming it.
No way. So if you see, I've got a telescope behind me here.
I do.
Yeah.
Yes.
And so this was supplied to me by our good friends at Oceanside Photo and Telescope. And so I'm going to be doing a series on the YouTube channel where I learn more about visual astronomy and astrophotography and teach people how to do it as well. So I've hooked up my DSLR to the end of the telescope, and now all I need is clear skies, which here on the west coast of Canada is not a very common thing. So, but maybe I'll do that during the meteor shower.
There you go.
All right. Well, so let's move on. Now we're going to have a bit of an argument. Not an argument. We're going to have a fruitful conversation about the discovery of dark matter by the
You mean a
Well,
shout
geez,
out?
all
by
the dark matter.
Chinese. So turns out the Chinese spacecraft, what's it called? The Dark
DAMP.
Matter Particle Explorer, or DAMP, has detected cosmic rays, and apparently there's a gap in the cosmic ray detection, and dark matter discovered.
Well,
There it
there
is.
you go. There you go. Problem solved.
Must
All the
be.
dark matter's right there.
Time to go home.
And
I'm
the
sure they've
gamma
already
detector.
bought tickets to
Great.
Stockholm next
Yeah.
year. They're all
Yeah, problem
Expect
solved.
that
We can all
3
go
a.m.
home now,
call.
right?
first class too.
But come on, they launched a spaceship to figure this out. They've got a spaceship. That's got to count for something, doesn't it?
So some
Yeah, I
people
mean-
launch a spaceship, other people go in a mine.
Yeah.
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 Different techniques.
So-
Or launch balloons.
So Paul, what did
Whatever.
what's going on here? What did they see?
So we mentioned things like already today, we mentioned things like the solar wind and the interstellar medium. These are made up of radiation, but also high energy charged particles, little guys like electrons and positrons. They're just completely flooding the universe from all sorts of high energy sources like supernova, like quasars. Just if it's energetic, it's going to spit out high energy particles. What we haven't really well studied so far is the incredibly high energy end of these cosmic rays, of these particles. And that is what this DAMP or however you want to pronounce it, satellite mission is designed to do, is to really focus in and get some initial results on that high energy end. And what they look at is basically, how many high energy particles do I get in this energy range, in this energy range, and another energy range? Just what's the spectrum of cosmic rays? And they noticed a gentle slope that agrees with other predictions and other measurements of the higher energy cosmic ray you're looking for, the rarer it is, which kind of makes sense. But they also noticed this weird bump in one particular energy bin where there's an excess, there's extra high energy particles of a particular energy that you wouldn't normally expect. That's the raw result. That's the data.
And how does that translate to dark matter?
Well, there are some models of dark matter where the dark matter particle, whatever it is, interacts with itself, produces high energy gamma rays, produces some exotic particles, produces some cosmic rays that would fly through the universe. And if the dark matter models are right and correct, and if these observations are right and correct and not just statistical noise, or they didn't make a mistake, then this could be a piece of evidence that there's this excess of cosmic ray signal that's due to dark matter doing some interesting exotic things.
Like, could be like blocking cosmic rays, or could be generating cosmic rays.
It would be generating cosmic rays.
Right.
By
But-
interacting with itself and annihilating.
But Paul, what if dark matter doesn't actually exist and we just don't know how gravity works?
Okay, so that's
Aw.
now the Kraken's been
The
released.
glove is down.
You know I had to ask.
I know,
Of
yeah.
course.
It
You see, in my flat Earth model,
What was it? It was the flat young.
the young flat electric
flat.
moon.
yeah.
Yeah.
So dark matter existing or not existing, or what we understand to be dark matter, whether it's a new component to the universe or whether it's modified gravity, that's one side of the discussion. Another side of the discussion is if we see something interesting astrophysical, like say a break in the cosmic ray energy spectrum at high energies, is that due to a dark matter particle, or is that due to normal, benign astrophysics just doing something that we don't expect? Or possibility number three, are the results junk? Is it just statistical noise that they're misreporting? Do they not understand systematics in their instrument, et cetera, et cetera, et cetera? This is going to require a lot more follow-ups. It's going to require a lot more theoretical studying before we say like, oh yeah, here was all along the evidence for dark matter.
All right.
Well, there you go.
All
I
right,
agree.
there it is.
Yep.
It's a result, and it's in
Yeah.
a Nature paper, so it's probably wrong. And the stupid thing is paywall too, and I went to look on the archive, the preprint archive, to pull up the free version, and I don't think they have a free version available.
No,
Not for
generally
Nature,
nature
no.
papers you can't put on archive.
Well, sometimes things will show up on archive first, and then they'll make their way to Nature.
Exactly.
Yeah.
Right.
Although the archive version can be super wrong because anyone can put their papers there.
It is slightly gated. So
Yeah.
nowadays,
Slightly gated.
to get on the archive, you need someone who is published a certain number of papers on the archive, so they're established or verified or whatever it is, and then they
Right.
can give you permission to also post on the archive.
Right. There's a bouncer to get into the room, but they're 4 foot tall and looking in the other direction.
Right. Yeah, I love the archive. That's like one of my favorite places to find stories. And it's surprising how often you'll find a story that actually goes really big, and that story was on archive all along. You
Right.
know, and
Yeah.
Or for like a year.
yeah, for
And
like a
then-
year. Yeah,
and
exactly.
It's been in peer review for a year, and it finally gets published.
Right. And so
Yeah.
you could have gotten the scoop a year in advance from everyone else. Take that hint, Kimberly, as your.
Oh, I know all about the archive. I got all the
No,
ins,
but as now that you're a
got my
journalist.
access.
Yeah.
For all the listeners who are just listening to all this inside baseball stuff, go to arxiv.org. That's archive.org. It's the preprint server. So basically, every physicist and astronomer and computer scientist and mathematician, and a few other fields in the world, they will submit their paper to a real life journal for peer review and publication. They'll also take that version and put it up on the archive for free so other scientists around the world can see it. You can read the papers yourself, and you can even subscribe to the nightly mailing list where you see every single, say, astronomy paper published that day.
Yeah.
Yep.
It's always fascinating to me to see how the number of papers fluctuates during the week, and especially around the holiday times. There's way more papers that go up on the archive during holiday vacations than you would
Yep.
actually
Is
but
that-
you know,
Is that because everyone's trying to
Free
get their
time as
paper out of the
well.
way so they can go on holiday, or they're hoping that everybody's going to have
no,
time?
it's because everyone actually has time to do it.
Yeah,
Yeah.
they
when
have
they're
time
on
to finish the
vacation.
writing before you can tell like different universities where the papers pop up a couple of days before classes start. You know, so you'll see
It's
this
really
spike.
fascinating.
That is awesome. All right. Well, I think it's time to wrap things up. Once again, we don't have a clever way to wrap up this show, so instead we're going to have to do some sort of shameless self-promotion of things that we've been working
Works
on.
for me.
Yeah. All right. So, person on my screen, Brian. What's something recent that you've done that people should know about that you haven't already explained?
That I haven't already explained. I would just say, I'm still gonna, promote Big Science. Go to Big Science on Facebook. That's the main thing. You can also look at bigscience.ca. It's Canadian, and go to the website there. So check it out, support it, love it, share it.
Right on. Kimberly, what's something new and fun that you just did?
So something really that I'm really excited about that's going to publish tomorrow morning on eos.org, that's eos.org, is a brand new section of our website that's all about the fun and quirky and weird things about Earth and space science. And so I'll be publishing the first article in that section. It's all about all the fun and quirky images that have been coming out of JunoCam, which is Juno's publicly available imager, that all the data are public, and just anyone as part of the community can download the data and process it and turn it into whatever they want. And there's been some really amazing and creative images that have come out of JunoCam that I'll be featuring in an article tomorrow. So I'm super excited about that. Go check it out.
Right on. Paul.
All right. Well, let me see. Thursday at 7 p.m., there is going to be a YouTube video dropping on my channel, youtube.com/PaulMSR, featuring a certain Dr. Koberlein.
What?
Talking
Whoa, who is
about-
that?
That's right. We did a collab video and it was awesome. We're talking all about the LSST and the challenges and opportunities of big data in astronomy. It's a fun show, and so I encourage everyone to watch it when it airs tomorrow at 7 p.m. Also, I have another announcement. Do I get two?
Yeah. Go
I
ahead.
get two. So we mentioned the Geminids. The Geminids will be on December 14th next year, 2018. one of the best places to see it is somewhere that's warm and also dry and dark, like the Atacama Desert. And you and I, Fraser, are going on a cruise in September. I'm taking a smaller group just by myself to the Atacama to spend a whole week of stargazing. It's a new moon, a week of the new moon, so it's totally dark. There's going to be the Geminids. We're going to visit the Alma Observatory. It's going to be a retreat for the lovers of the sky. So go to astrotours.co/Atacama.
And
You know,
will...
you could use someone who knows the southern sky.
Yeah, we'll talk. Okay, we'll talk.
Okay.
Well, and you're going to go and scout out and find out if we can, what it's going to take for us to be able to view the eclipse in 20.
Yes, because the
right.
July 2019 eclipse is
2019.
coming through
Yeah.
just south of the Atacama. It's coming through the Elqui Valley of Chile. Actually, Fraser, I just had a very interesting meeting a couple days ago. That trip is in the works.
Right on. I can't
Don't
wait.
worry about that.
Brian's got his glasses.
I do.
He's ready. So my just piece of news, I got a new episode of The Guide to Space going live tomorrow. It's a collaboration with me and John Michael Gaudier, who is a really cool science fiction author and astronomy explainer, and a lot of people are big fans of his work. So if you like Isaac Arthur's stuff, you'll like John's. And I know you just did a collaboration with him, Paul.
That's right. That was huge. So
Yeah.
John Michael Gaudier, something's really awesome about his channel because he has like 25,000 subscribers, but each video is 10 to 20,000 views. Like
Yeah.
the people who follow him really, really eat his stuff up. And I think that's really fantastic. I'm really excited for him. Very, very lucky to do a collab video with him.
And my patrons have already seen the video, but it drops tomorrow, so that's happening. All right, well, let's wrap things up. So, as always, thanks to all of the co-hosts for joining us on this Weekly Space Hangout. Special guest, Brian Koberlein. Brian, thank you so much.
Thank you very much.
And big thanks, as always, to the Weekly Space Hangout crew. They are the people who provide this chat down at the bottom of the show. And if you want to join that, just go to wshcrew.space. It's all free, but to that you will then become one of the executive producers of this show and help book guests like Brian Koberlein. That's how this works. All right. Let me shift to the big view. There we all are. Everybody say goodbye. Thanks, everyone.
Bye.
Bye.